Welcome back. We're going to mess around with outliers and how that affects the least squares regression line today. Again, as you can tell from the poor job I'm doing of making sure my words match up with my lips, this is the last of the poor sound quality options that we have. So what we're going to first have to do is we're going to go over to a regression applet from our textbook. And what you're going to do is you're going to add points into this graphic area, I believe, to get a regression, an R-squared value of 0.4. The correlation coefficient, remember, is your R-squared value. So as you type this 2 points, you're going to get a correlation coefficient of 1 because you only have how many points make a line? 2 of them, right? All right, so as you add these, you're going to try to, again, drive that correlation coefficient to 4 or 0.4. Now, interestingly enough, you're going to end up having to get them in a somewhat straight line pattern, but can't necessarily, it takes a little bit of practice. You don't necessarily can do it right off the box. And the closer that you're in the middle of the pattern, the closer you're going to help. It's generally going to raise and get you closer to 1. So apparently I'm having issues, but you're not the only person who's having issues with this, obviously. So 5 more points, Mr. Hayes. By the way, yes, this is Mr. Hayes from Hayes' World of Math. And there we go. Okay, so we're close enough. So then what you end up doing is you're going to say show the mean X and Y line. So it's going to average all the X values and average all the Y values. And it's also going to show the least squares regression line. And when you do this, notice the regression line goes right through the middle of the means. And if you think about what's going on, it kind of makes sense because you're kind of averaging things out. So we're going to do a quick sketch here below. So we're going to go through and we're going to make 4 points. We're going to make one on the far right-hand side of the graph on the horizontal line. So we're keeping the Y. So this is not going to change your Y mean score. It's just going to change X value scores. And so we're going to see what happens there. We're going to check both the slope and the y-intercept in addition to the correlation. And apparently I'm being extremely thorough with that. So we're going to add one way over to the far right-hand side, call it A, and let's see what happens. So if we go way over to the right, notice what happens is that the correlation dips quite a bit, going from 0.4 down to 0.1, 0.1. The other thing that notice obviously happens, and by the way, if you click on the points themselves, it'll remove the points. So you can kind of go back and forth. Obviously, the slope is changing, as well as your y-intercept. The y-intercept is going up, your slope is pitching down. And this is all stuff that, again, you would normally do on your own. And if you're a teacher watching this, you can probably have your kids do this remotely. Or at least do it all together. So the slope decreases, the y-intercept increases, the correlation also decreases. So now we're going to do the same thing. We're going to put it way over here on the left. So notice you get kind of the same result. Why is the one on the right having a bigger effect? Correct. Simply just the distance away from the mean point. Mean X, mean Y. Or you can say X, mean Y, mean, I suppose. But it's a pretty similar idea of what's going on. So the slope is decreasing. The y-intercept increases. Correlation also decreases. So some people are not surprised that it's the same thing all the way across. And again, there, I think I'm trying to do hand signals to say it's a matter of scale. A is further away than B, so A is going to have a bigger effect than B, which again, it's an outlier. Not super surprising. The further away your outlier is away from your mean, the bigger effect that we had. And we saw that back in chapter 1. for sure CED unit 1. So now what happens if we do it on the X mean axis? And apparently, there we go. Nope, getting ahead of myself. So we're going to go below the least squares regression line on the vertical line X. So we're going to actually go for the smaller distance here. So we currently have a correlation of 0.4141, and it drops down to 0.326. But interestingly enough, look what happens to the slope. Nothing's changing. You're just changing the y-intercept. The same thing happens when you go up on top. Correlation coefficient goes down, but the rest, and the y-intercept changes. It drifts towards the outlier, but the slope is staying the same. And think about what's going on. You're dealing with the change of y over the change of x, right? If you're adding in a mean value of x, you're not really changing it that much. So anyway, so same, decreases. And we'll have same slope, increases the y-intercept. Nice catch, Mr. Hayes. So which outliers have the greatest impact on least squares regression, the vertical or the horizontal? Good question. So the horizontal ones change everything. So it tilts the line. Mr. Hayes, switch the camera back. Mr. Hayes, switch the camera back. Switch the camera back. There you go. Good job. All right, so the first one's tilt the line from the XY, X mean, Y mean point. The other one's changes the y-intercept from X1, Y1. Ta-da! And again, so if you're off of it, off of either the X mean, Y mean lines, you can get varying effects, obviously. Also with the more of what you have. All right, so which outliers have the greatest impact on the least squares regression line? Horizontal? They have more leverage since they are to the left and right. So you're actually pulling things down and you're not above or below. It's kind of like if you were on a teeter-totter, if you remember what those are. For those who don't know, it's a plank on a piece of a pivot point on a playground. If you're standing right on the pivot, you're not going to have much of an effect. If the further out you go, the more leverage you can go ahead.